Hello everyone, welcome to our presentation DeepCAD, a standalone deep neural network based framework for classification and anomaly detection in a smart healthcare system, which is recently got accepted in International Conference on Digital Health 2022. The paper is authored by me, Nur Imtiazul Haq, Dr. Mohammad Ashikur Rahman, and Sheikh Iqbal Ahmed. So these are the contents that I'm going to cover throughout my presentation. At first, I'll give a very short overview of smart healthcare systems. Then I'll go highlight the main motivation of the work along with existing state-of-the-art researches. After that, I will illustrate the proposed framework, and at the end, I'll demonstrate the main experimental results before concluding the presentation. So the smart healthcare system concept is reshaping the modern digital healthcare system by making it more personalized, automated, and effective by incorporating the Internet of Medical Things enabled network. In a typical smart healthcare system, patients are automatically being treated with implantable medical devices or other automated medical delivery system like heart pacemakers, drug infusion pumps, etc. And these medical actuators are triggered by a control signal which is primarily provided by a cloud-based controller. The controllers mostly use machine learning based algorithms to determine the patient's status through wireless body sensor devices connected to patient's body. An example smart healthcare system is shown in the figure where a patient being diagnosed with both COVID-19 and diabetes is remotely being treated with automated actuation of the ventilator and the insulin pumps. The recent pandemic period has highlighted the need for a smart healthcare system most, since almost 48% patients of United States got denied or delayed treatment, and 11% of them have experienced deteriorated health conditions. Deep neural network based smart healthcare system controller has attained significant popularity in the recent days for patient health status classification due to their intricate pattern identification, nonlinear boundary acquisition, and interfeature relationship capturing capability. The accuracy of deep neural network models largely depend on the amount of training data. However, the prevalence of more than 2,000 exabyte of healthcare data, mostly connected by Internet of Medical Things enabled network, supports that the healthcare has become one of the mature safety critical cyber-physical system, and the data collected from the healthcare network can be used for training the deep neural network models accurately to classify the patient's health status. The smart healthcare system is exploited or feasible to be exploited with several attacks, including the hardware Trojan, man in the middle, malware injection, civil attacks, denial of service based attacks, and so on and so forth. Recent healthcare statistics and researches have created significant security concerns for smart healthcare systems. For instance, more than half of the healthcare organizations have been affected by adversarial attacks from October 2018 to October 2019. A report states that the University of Vermont Medical Healthcare Center got isolated from network connection due to a cyber attack, which is estimated to incur almost $64 million loss. One of the research has identified that 15 to 20 Internet of Medical Things connected devices contain 6.2 vulnerability score. Although deep neural network models mostly classify the patient health status correctly, knowledgeable adversaries with the knowledge of deep neural network model can misclassify the patient status and can deliver wrong treatment to the patient through adversarial machine learning based attacks. Moreover, the deep neural network models being trained with benign data only classifies each and every possible predicted sample as the learned classes. It cannot classify the predicted samples as anomalies. Due to the increasingly growing zero-day attacks, learning the attack pattern is not also possible. Being saying that it is crucial to provide anomaly detection capability to the smart healthcare system controllers. So here are the overview of related works for our research. As I said, for classification of patients' health status of a smart healthcare system, supervised machine learning models, particularly deep neural network models, are adopted. However, for anomaly detection, the existing research propose separate anomaly detection models mostly. For instance, the outlier and transfer learning based anomaly detection techniques have grown increasing popularity in the current healthcare research and security researches. In one of our works, we assembled two unsupervised machine learning models, naming autoencoder and one-class SVM for anomaly detection. In another work, we have proposed two separate machine learning models and we optimize their hyperparameters using bioinspired optimization-based techniques for classification and anomaly detection. However, the incorporation of two separate models add latency to the control decision making, which is critical for safety-critical cyber-physical systems like smart healthcare system. So to the best of our knowledge, no existing work can directly add anomaly detection rules to the deep neural network based classification models. Although there are some frameworks like DeepCTRL that can add rules, their rule addition follows a very specific pattern and anomaly detection rules cannot be directly added using those approaches. To address this problem, we have developed deep neural network based classification and anomaly detection or DeepCAD framework that can perform both classification task and anomaly detection task without being trained with the anomalous samples. Moreover, the DeepCAD framework does not require a separate model for anomaly detection. The robustness of the deep neural network model of DeepCAD framework is analyzed against adversarial machine learning based attacks. The proposed DeepCAD framework is verified on two real datasets, naming Pima Indians diabetes dataset and Parkinson disease dataset. So here we present an overview of the proposed framework. We created a synthetic dataset for intuitive understanding of the workflow. The dataset contains two classes of samples, positive and negative. The sample from the positive class are colored as green and negative class samples are colored as red. The principal task is to classify the positive and negative samples correctly. And it is clear from the figure that the same samples are separable with a very simple boundary. And a regular deep neural network model can accurately perform the classification task. However, since the model will be trained on two classes of samples, the trained deep neural network model will classify any data point into those classes only, irrespective to their belonging to the data distribution. Our proposed framework solves the problem by classifying out-of-distribution samples as anomalies. The first step of our framework is data preprocessing, and we use principal component analysis technique for dimensionality reduction of the data space, feature space. In this proof of concept work, we consider that like two features are available after the dimensionality reduction. After that, all preprocessed data are passed to Welch's algorithm to obtain a minimal circle, encircling circle that can enclose all the data points, such that a circle with the least possible area that can bound all the data points. Initially, the framework encodes the label of positive samples as 1, 0 and negative samples as 0, 1. However, the labels are scaled and normalized after boundary acquisition according to the circle center or boundary distance. So after the scaling and the normalization, the positive samples close to the boundary are labeled close to 0.5, 0, whereas the negative samples are labeled close to 0, 0.5. Similarly, the positive samples near the circle center will be labeled close to 1, 0, and the negative samples will be labeled close to 0, 1. The points in between are scaled accordingly. The purpose of this task is that the points that are out of the boundary defined by the Welch's algorithm are labeled less than 0.5, and when it will be rounded, it will become like 0, 0 and such that it will be counted as an anomaly. To make the anomaly detection performance better, some additional samples are added to the training dataset in a way that those close to the boundary points are labeled slightly less than 0.5. The final step of the proposed framework is model training. Although the problem is a classification problem, the deep neural network model of our framework views the problem as a regression problem. The deep neural network model takes the preprocessed data as its input, there are 2 input features and 2 output levels for the deep neural network model. The number of layer and the number of hidden layer nodes are later tuned for optimal model acquisition. From the figure, we can see that after initial passing, such that without training, the model misclassified almost each and every sample. The deep neural network model is trained for several epochs, and the weights of the deep neural network model are tuned in each epoch based on a loss calculation. We consider here the mean square error as our loss function to determine the mean difference between the actual and the predicted samples. The loss calculation is also supplemented by calculating errors between out-of-boundary verification samples with their model prediction, such that verification loss function. The later loss function is passed through a ReLU activation function. The framework at the end outcomes the model that has converged. So after the model training, you can see that no samples outside the MEC are labeled as positive or negative samples. So here is the performance of the classification task of the DeepCAD deep neural network model. So you can see that for both of the dataset, which are the Pima Indians diabetes dataset and Parkinson dataset, the DeepCAD deep neural network model is showing almost similar performance as a regular deep neural network model, which is perfectly tuned in terms of the accuracy, precision, recall, and F1 score. So here is the performance of anomaly detection task of DeepCAD deep neural network model. So in the left hand side, we can see a pre-processed Pima Indians diabetes dataset. And in the right hand side, we can see that after being trained, the DeepCAD deep neural network model is successfully labeling all the data points outside the minimum enclosing circle defined by the OLG's algorithm as anomalies. We evaluate the robustness of DeepCAD deep neural network model by assessing the performance of the model against adversarial machine learning based adversarial samples. Here we considered fast gradient descent method as the adversarial machine learning based attack. Here we use accuracy drop as the performance metric for robustness analysis. The adversarial samples are generated from regular deep neural network model with different attackers' capability. It can be clearly depicted that the accuracy drop of the DeepCAD deep neural network model is significantly less than the regular deep neural network model. So here are the concluding remarks and possible future works. So in this work, a novel deep neural network model training framework naming DeepCAD is proposed that can perform both classification and anomaly detection for a smart healthcare system, and thus can deal with the latency issue of the smart healthcare system controller. The proposed framework is verified on 2 real datasets, naming Pima Indians diabetes dataset and Parkinson disease dataset. Our experimental analysis shows that the DeepCAD deep neural network model experiences around 50% less accuracy drop compared to regular deep neural network model against adversarial machine learning based attacks, here in particular fast gradient descent method attack. Although the proposed work is a proof of concept work, this work can be extended and or can be scaled. For instance, here we considered OLG's algorithm to draw a minimum enclosing circle. However, OLG's algorithm can draw minimum enclosing n sphere. Hence, high dimensional features can be considered for our work as well. Moreover, we considered only in sphere or minimum enclosing circle in our work. However, any shaped boundary can be used by extending our work for encircling the points and performing the anomaly detection in a better way. Although we considered binary classification problems in our case, our problem can also be extended for multi-class classification settings. Here we consider deep neural network based models only. However, the work can be extended to allow different machine learning models, and we'll be testing those models against a wide group of adversarial machine learning based attacks. Thank you so much for listening to my presentation. If you have any questions, queries, or confusions, please let me know. I'll be happy to answer.